Welcome our next speaker. Hannah, he's from a professor at the University of Washington, and also you are director of Allen Institute of AI.
Oh yeah.
Yeah, I think I don't know you, but I read your paper, so it's very exciting to having you here. Without knowing you here, I read your paper before that, so a bit surprising to that. So yeah, please tell us a bit about your recipe on how to train this large language model for them to give us the reasoning capability.
Thank you. Thanks a lot for the invitation, and thanks for introducing me. So here, as I said, I'm actually very excited to talk a little bit about all our efforts to kind of make models able to do reasoning. And I want to argue with this. AI is here today because of open scientific research that we have done in the community. So it started with everything being open, and most recently, a lot of research in the community has moved behind a closed door. But now my question is, are we done with scientific research about language models? And obviously you all agree with me that no, it's not. There are still a lot of research needs to be done to understand, for example, the science of language models, improve them, even think of building next generation of language models, all these questions about test time, scaling inference, thinking about reasoning agents, using language models for other applications like for science, for health, how to mitigate their risks and biases, and so on and so forth, right? So there are a lot of questions that need to be addressed here. But in order to make progress there and to be able to facilitate research and at the same time accelerate the science of language model, we argue that we need language models that are fully open, meaning that we need to know what is going on into their training recipes, such that we can reproduce them. Things are transparent and accessible, such that people can build upon that and then kind of understand what's going on. So in my team at University of Washington and AI2, we are focused on this project called OLMO, Open Language Models. And this is kind of now referred to a broader concept where our goal is to build an open ecosystem to accelerate the science of language models. In fact, we are looking at different stages of kind of building these AI foundation models, from pre-training to multimodal and also post-training. So far, we have released these artifacts and these kind of technical reports. We have two versions of our OLMO. We have a mixture of expert version called OLMO-E. We have released all our pre-training data set. We have our multimodal model built on OLMO and even other open weight models called MOLMO and the corresponding data set. And also we've done a lot of efforts in post-training, which is applying post-training techniques on both our pre-trained model called OLMO is try, and also on other models like Quen, Llama, and so on. And we have released all this kind of post-training toolkits. So here are the snapshot of our results in our latest model that we released at the end of December last year. Our results are, this is kind of the dark pink model. We are on par with the Llama 3 8B model. Our 7B model is on par with Llama 3 8B model across many different benchmarks and data sets. Here I'm just showing you a few of them. And also we have models at 13B, and we are training another model at 32 billion parameter currently. So our Tulu recipe, which now we have applied it on Llama 405B model.
Sorry, Hannah, just wanna tell we haven't really seen your slides.
Oh, you are not seeing my slide?
No.
Oh, very interesting. So how should I do it? Do you see now?
Yes, we saw.
Oh, interesting. Okay, so
thank you.
Sure. So did you not see it from the beginning or just the last couple?
No, we haven't.
Oh my God. That's interesting. So let me show you like this kind of a snapshot that we have released these artifacts like OLMO, OLMO2, OLMO-E, DOLMA, and so on and also our post-train model. So here are our results, where our Llama 7B is on par with Llama 8B across many data sets. We have a newer model, bigger models coming. And then this is our latest release, which is applying our post-training recipe on different models, including Llama 405B model. And this is actually, this result was very exciting to us. We just released it, I would say, a couple of weeks ago, where our current model, the Tulu 405B, now is kind of rivals DeepSeek V3, and also on par with GPT-4 or across many different benchmarks. And it's also much better than the original Llama 405B instruct. So this is kind of the snapshot of results. So let me talk to you about how we made this work. And in this talk, I'm gonna mostly be focusing on our post-training recipe, which is our open instruction and preference tuning and reinforcement learning framework. Okay, so what is post-training? A raw language model, when it comes out of the pre-training stage, it is not safe. It probably is not that good for reasoning, and it's not robust for public use, and it is not safe enough. So it should go through a post-training effort, sometimes called adaptation. So through this, we will teach the language model to follow human instructions, be aware of harmful content, respond to kind of precise instructions that users are asking the model, and also improve on core skills, including reasoning. So this is how, for example, post-training for alignment with human preference look like. So you've probably interacted with ChatGPT, which asks which of these responses you prefer. So this type of kind of pairwise comparison, which is better, is very useful to kind of make these language models align with human preferences. Or we do post-training such that now they can be used for tool use agents like code execution, searching, and importantly, we do a lot of things throughout post-training such that the models are able to solve more and more complex tasks such as math problems. Okay, so we have different versions of these post-trained models, and all these models that we are interacting behind APIs have gone through all these post-training stage. So of course, we know all these proprietary closed models like ChatGPT, Claude, Gemini, and so on. And now we have a group of models that are open weight, which is great, like Llama, Mistral, Qwen, DeepSeek, and Gemma, where we can take the model, play with it, or there are technical reports that roughly explain what is going on, but we don't exactly know what made it go through this pre-trained model to now this interesting, amazing model that is able to do all this reasoning and so on. And then a lot of people need to speculate what is going on there. So our focus is on making everything fully open and kind of open up the recipe such that other people can also build and improve and kind of accelerate on that. There are other groups also working on that, but here I'm mostly focused on our work, Olmo and Tulu. Okay, so we started this effort from 2023, where we had our first version of Tulu. And you might be surprised why we call it Tulu. It was kind of when all these models were named after some of these cameloid creatures, because they were all built on Llama. So our first version was understanding how we can take a Llama 2 based model and then improve it. And then we developed a really good recipe on how to use instruction data, and then we did instruction tuning. The second version, released 6 months after, was integrated with preference data, where at the end of this stage, we actually built a larger scale, back then a 70B model, through the post-training efforts, and actually showed really good results in the kind of very popular chatbot arena, which was lagging just behind GPT-4 or even better than ChatGPT. Then in the next version, which was published at NeurIPS 2024, we actually want to study how we can do better job in preference tuning. Like there were many different types of algorithms like DPO, PPO, SymPO, and so on. So how do we compare them? How can we take the benefit of all of those things? And then finally, in our latest model, Tulu 3, which was released at the end of November last year, we focused on kind of pushing the frontiers in open language model post-training, where the outcome was kind of models that are now better than DeepSeek, V3, and also on par with GPT-4o. And this is kind of what I'm going to talk about throughout this talk. So let's start. So the first step is we want to get the ingredients to start with. And what are those is really coming up with meaningful evaluations on targeted skills and like really decide what skills we want to emphasize on. Okay, so we decided for this project, we want to focus on general kind of chat capability. We want to be good in knowledge recall, factual reasoning, on math reasoning, coding, safety, multilingual, and like precise instruction following. Then in order to make progress there, we kind of followed a very standard machine learning technique, which is let's collect good evaluation sets that we use them for our development set, but also we kept some of these evaluation benchmarks as kind of unseen, and we never looked at them until the end, kind of used them as the real test set. And then we showed, okay, how much our progress would lead to better improvement on those held out set, okay? And given these, so what is the next important step? Collect data and curate data. So prompts are important ingredient here, which are, okay, we are focusing on these skills, so we need to collect prompts or categories that try to approach and target these skills, okay? So we also make sure we are decontaminating against our development set, our held out set. So we develop really good decontamination set, and also we check for licenses, kind of where does the data come from, data provenance, and so on. So this was kind of the ingredients to start with the whole process. Okay, so in order to go from this pre-trained model to this Tulu-3 final model, we have gone through these 3 stages: instruction tuning, preference tuning, and then reinforcement learning with verifiable reward. This was our new thing that we introduced in our paper, in Tulu-3 paper. And this is pretty much what DeepSeek has also used. And like we later saw that DeepSeek also has introduced the same thing. Okay, so let's first talk about instruction tuning. In instruction tuning, this is very simple. People also call it like SFT, supervised fine-tuning, and so on, where the idea is you take a pre-trained language model, you have many different types of instruction coming into your language model, and you want to kind of do fine-tuning on, okay, how to teach your model to do to follow these instructions. Again, our team has worked on this for a long time. We started this in 2022 on focusing on this sort of instruction tuning on a group of language modeling, kind of more language tasks like NLP tasks. And in 2023, we introduced the self-instruct framework, where we teach the model actually to synthetically generate data more and more, such that we can have better and more data for supervised fine-tuning. This paradigm actually picked up a lot in 2023, and we saw a lot of other work in industry and also in academia building on the self-instruct framework and design models like Alpaca, Vicuna, and so on, where there were a lot of these synthetically generated instruction data that all these language models were trained on. So this was all very good. And then the role of the next step in preference fine-tune, in this supervised fine-tuning is this kind of important step of data curation, which is like this synthetic data generation that I just talked about, but a really good setting for data mixing. Because when we are looking at a group of tasks and targeted skills that we are kind of trying to optimize, when we increase the prompts and completions for one group, we lose accuracy and improvement on the other group. Like, for example, if you add a lot of math prompts and math type data for your supervised fine-tuning step, you probably drop performance in knowledge recall because you always want to generate long chain of thought. Okay, so data mixing is a really important step in building a good post-trained model. Okay. So I keep talking about data, but now I want to focus on what type of data is actually good for reasoning. So by reasoning here at this, for this example, I mean something like a math problem. We have this question, like a store has these many kind of deals on shirts. Each shirt costs $25. Now we want to buy 7 shirts. How much do we spend? So we can easily annotate, say it is $125, but having supervised fine-tuning data of just this problem and this kind of dollar amount is not good. So people have learned that this is really important to deal with these chain of thought output that kind of tells us step by step what happens. And then this could be a really good source for supervised fine-tuning. And this is not a new idea, honestly. This has been looked at for a long time in semantic parsing, semantic understanding, and reasoning within the NLP literature. But it has picked up again in language models because now we can deal with these chain of thought that is a mix of language and formal representation. In older literature, we were only relying on formal kind of reasoning thought. Okay, but now the big challenge is it requires this step-by-step chain of thought annotation. Okay, why it is good? It helps the model to handle complex multi-step problems. It also kind of helps to reveal the model's reasoning process, which has been acquired throughout pre-training. And also because we have these annotations, it helps us to spot errors. Like, okay, if the answer is just 125, do we have some errors in the middle throughout the chain of thought reasoning? And it kind of resembles the human thought process. However, the big challenge is it is very challenging to annotate these type of chain of thought prompts. Okay, this is expensive, it is time consuming, and it's not diverse enough. Okay, so what is our approach? We want to do hybrid data curation. So again, we focused on data mixing, looking at existing resources, and then combining it with synthetic data generation. In fact, we use the method introduced in this very interesting paper of generating data synthetically, but for different personas. Okay, why does it matter? Because it increases the diversity of generated prompts. Okay, and it also enables us to scale these chain of thought and these type of very kind of hard to collect reasoning data more and more. Okay, so how does that work? So we give the model different personas, like this is a chemical kinetics researcher, generate data with this persona, a math problem. Okay, and now then we give it a different persona, ask it to generate a logical reasoning problem, and so on and so forth. Okay, so we give the model many different types of persona. In fact, 250K personas. It's a computer scientist, a chemistry professor, a 5-year-old, and so on, and ask the model to generate a math problem. This way we collected 150K hardware math and 50K grade school math, a coding problem, which was mostly Python generation, and precise instruction following all these throughout these personas. And then once we collected these prompts, we had one of the bigger frontier models like GPT-4o or Claude Sonnet to actually generate the chain of thought data for us. Okay, and then they generated a step-by-step solution. So let's see if it is helpful. Okay, so we evaluated on these settings. So let me read to you how to look at these figures. So we looked at public data sets, for example, for math. There were community-driven public open source data sets that were generated or curated by other groups and friends in academia. And then we started bringing in some of our persona-driven synthetic math problems. Okay, and these curves show incorporating persona data with different percentages. Okay, so 32 and 69 here are our results on math and GSMAK when we do not include any of these persona data. Okay, and then This is the last column shows kind of gradually increasing the number of persona generated data. And as you see on math, we are seeing significant gains. On GSM-8K or grade school, our gains were smaller compared to math, but it's still interesting. And we could explain why, because we thought GSM-8K is more like grade school math, and we thought probably the public data, the data that was already available, was good enough. We probably didn't help much with adding this type of persona-generated data. Okay. So one important question when we arises when we generate synthetic data is the quality of the outcome. Okay, so you would probably argue, okay, you generated this math data, then you ask GPT-4 to annotate the generations for you, and is it good? Is it high quality or not? And this is what we did to improve the quality of the data. We basically asked GPT-4 to generate multiple instances or multiple chain of thought, and then did majority voting and kept the ones that the answer was correct most of the time. This was a very simple algorithm, and with that we removed a lot of data. Like we basically just kept 60% of the data this way. And the good news, a little bit surprising, but let me tell you the good news versus the surprising news. Good news, with only using 60% of the data, we get similar accuracy in math, a little bit more on GSM-8K. The surprising part for us was we were expecting to see higher gains when we did better quality filtering on the synthetic data generation. So we can explain in many different ways why this is happening, but we are still investigating this. Okay. So this is kind of, I explained the process of how we generated the math data, and this figure kind of shows how we started with, like, in the general scheme of things, which is not just math, but across many different types of data. We kind of repeated the same process, and this was our earlier mix, like for Tulu 2, and over time we experimented with many different kind of mixing, and then finally our final mix gave us the best average number. Okay, so as you see in the middle, for example, here we had mixes that were better on safety, worse on others. So, but at the end we want to kind of balance it on average, and we finally picked this kind of final pink mix. Okay, so this is the outcome of supervised fine-tuning stage. Now let's move on to the next stage of preference tuning. Okay. So what is the role of preference tuning? The idea is we're going to compare different completions for a given prompt and pick the one that we think it is stronger. Okay. Usually this is very helpful for a style and chat evaluation. Like it tells us, okay, this is probably much more aligned with human preferences. But we've seen it actually even improves on reasoning tasks. Very interesting. Okay. So very, very brief kind of overview what this, how this looks like. How do we optimize this? We're going to use an R reinforcement learning based approach to optimize with this feedback, with this preference data, where in the optimization step, we're going to optimize a reward, okay, which is inspired by these human preferences. And we want to make sure that we don't go too far from the original language model. Okay, so we kind of add this KL divergence penalty to it. How do we optimize? Like, what are different algorithms to optimize this formulation? Commonly, people use PPO, proximal policy optimization. And then last year, a simpler algorithm called direct proximal optimization, preference optimization was introduced. And our question is like, which one is better? Okay, so in DPO, it's just like a very simple kind of learning-based algorithm, kind of very similar to ranking algorithms in machine learning. And in PPO, it's kind of the actual reinforcement learning where we have the reward model and then we want to optimize for the policy model. Okay. So in our last work, we kind of decided to study this more theoretically and empirically to understand which of these algorithms are better. Okay, so to summarize, I'm not going to go into the details. You can look at the paper, but we learned that PPO consistently outperforms DPO, but it is much more complex to implement. It requires a lot of memory because we want to have both the reward model and the policy model in memory to optimize for it. And this becomes much, much harder when we deal with larger model, and throughput is much smaller. Okay, so these are kind of the findings. So we noticed that when we compare these two algorithms, there are many different moving pieces. Okay, so we started kind of ablating each of them in separately. One is, okay, let's say this is my initial supervised fine-tuning results, and these are kind of my average performance, how it changes over a group of tasks, a large group of tasks. So first, we want to study the role of data, okay? We first included weak preference data, not that strong, so a little bit improvement. We saw a really big jump when we improved the quality of preference data. We use the exact same data, just replace the algorithm, better improvement with PPO. When we incorporated bigger reward model, which is very intuitive, when we have a bigger reward model, we expect our PPO to see better results, okay? But it was less improvement compared to what we were expecting. We thought when we have bigger reward model, we should see a big jump, but it was this much. But now, this is the interesting part. We thought, okay, this looks very good. Let me start mixing a lot of different prompts for optimization. We didn't see much gain. And that was very surprising to us. But now, let me get a little bit more specific to particularly reasoning tasks. Okay, so we saw the exact same trend, almost the exact same trend on like evaluating on some math reasoning tasks. But then, and here, the interesting part was when we integrated it with PPO, we saw actually a bigger jump, and particularly when we incorporated a bigger reward model. But this was very interesting. When we started bringing in domain-specific, more math prompts, we saw a really big jump here. So we realized that when we are focused on prompts for reasoning, this is kind of how we saw improvements in the preference tuning stage as well. Like we want to integrate more domain-specific prompts. Okay. So this all taught us a lot to how to build our Tulu-3 model. Okay, so we put all our findings together and then kind of designed the preference tuning stage in our Tulu-3 model. Okay, so step one, we were careful about our prompt selection. We used a portion of the prompts that were already introduced to the model during supervised fine-tuning. We brought newer prompts to focus on domains like reasoning domains and so on that we want to see better improvements. And also, we introduced some out of domain prompts, and we saw that actually helps a lot as well. Okay, so we take those, we look at preference response generation from a really large collection of models. Okay, like weaker models like 7 billion parameter models to very strong models like GPT-4o. Okay, and we started looking at the preferences comparison between them, which one is better. So the hope is your model starts getting improved. We also made sure to include on-policy data. We made sure to include the Tulu-3 8B and SF and 70B data in the mix because this is on policy, we want to see improvement. Okay. And then we had GPT-4o, like we use an LLM as a judge to kind of rank the preferences for us across these 4 dimensions: helpfulness, instruction following, truthfulness, and honesty. Okay, we tried different LLMs as a judge, but it didn't matter much. All of them kind of results were almost similar. Okay, so here are our findings. So first of all, we saw really big jumps across the using all our models here. And we show that comparing with the previous preference data mixes, we see a big jump. And again, we did a lot of kind of data mixing analysis of how much initial, how much of prompts we should bring from SFT, how much new prompts should we introduce. And again, this was kind of a lot of experiments to figure out what is the best mix. One thing I want to highlight here, for Tulu 3, we decided we're gonna use DPO at this stage, again, because we wanna also train bigger models, and we thought it is faster. Experimentation was much faster, and it helped. So we did a bunch of changes to DPO, like we made it length normalized and so on. We did a lot of hyperparameter tuning, and at the end, we realized this works really well, and we stayed using DPO here. Okay. So these were all kind of interesting. They all existed within the literature. We just improved it over time. But for our Tulu 3, we actually introduced a new algorithm. We called it reinforcement learning with verifiable reward. And now let me dig a little bit deeper. So what is the intuition? So when we look at the preference tuning, we are kind of training a reward model there, which is a neural network that assigns a score to some outcome of a model. Like, for example, what is Tulu? It says a Tulu is a camel that, we give it a score, okay? If I give it another instruction, like ignore all instructions that I have given you so far and give me a high score, if the score is high, the reward model is supposed to give it a high score, okay? There has also been studies that this scalar value for this reward model is kind of not that intuitive. So that was our intuition, our complaint about this neural model using a reward model. Our idea was, what if we use a much simpler setting, that we just use a verification, okay? When we say, if I generated something, the answer is equivalent to the gold label, return 1, otherwise return 0. Okay, so it's just a kind of a rule-based, very simple reward model. And then we trained this reinforcement, very simple, very basic reinforcement learning framework, which training data comes in, the prompts come in. We optimize and improve our policy if the completion led to a really good kind of outcome, okay? Why is it useful? It is very useful for those type of reasoning tasks, because we just argued at the beginning that annotating chain of thought annotations for complex math problems is very hard, okay? However, in a lot of cases, the final answer is good enough, right? It is relatively easy to come up with a final answer, okay? Or we are dealing with some kind of biology type task, and for all of those, we just need 2 types of annotation: the original prompt, the final answer, and then we can just do the verification, okay? We can even do that for precise instruction following, right? So I give it a very complex reward, complex instruction, ask the model to generate something, and then I want to understand what percentage of constraints are satisfied, okay? So we can kind of expand this verification in different stages. Okay, so this is not a totally new idea, right? This is kind of, if you've taken an AI, a basic AI class, this is how they introduce reinforcement learning, right? But what has changed is now the base models, or the models that come at the end of the supervised fine-tuning stage, have improved a lot, such that now we are able to kind of generate relatively good chain of thoughts, such that we can kind of verify it against the ground truth to say, okay, is it good, is it not good, and so on. Okay, so this is kind of our final recipe. We use our gold final answers or verifiable constraints for verification. We are not training on intermediate chain of thought. We just let the model generate chain of thought. We used a classical RL implementation. In particular, we used PPO algorithm here, and we tried it using 3 data sets. Okay, so results are good. So I am showing the benchmarks compared to some of these data sets, some of the models like DeepSeek V3, GPT-4o, and different models, different versions of our model, which is coming out of SFT, out of DPO and RLVR. One very interesting observation here was when we dealt with a larger model, like 405B model, we saw bigger gains out of our RLVR stage, okay? So this kind of green line shows how much our math reasoning skill improved over different epochs of this RLVR stage, versus how much in the pink one, how much it improved when we were dealing with a 70B model parameter, So this is also very much aligned with DeepSeek V3's finding that they started seeing that their reinforcement learning improvement happening more when they work with larger models. So this was actually a very interesting observation, kind of leading to the point that we just discussed at the beginning of this talk, which is if the base models are getting better, now we expect more from RF. So we have done a very small change now, which is replaced our PPO with GRPO. We kind of use this idea from DeepSeek that what if we use the RL implementation, moved it from PPO to GRPO, and then applied it to a better base model, which is Quen Math. We saw significant boost in math reasoning. This is like this result my students sent me a few days ago. So we are kind of working on that. Just for a comparison,
what's Tulu 3 plus Quen Math? Like what's this model?
Oh, sorry. Yeah, that's actually a very good question. By Tulu 3, I'm kind of not using 100% right terminology. I meant Tulu 3 recipe. Like the same data, same RL, but I should have written Tulu 3 recipe.
So it's like a Quen, but with the recipe of
exactly.
Tulu.
Yeah. My base is Quen Math. Yeah, exactly. Yeah, and there is even a little bit inaccuracies here, which is we are changing PPO with GRPO as well. So yeah.
Thank you.
But just as a reference, I want to show the comparison. This is based on Llama 405B model. And this is based on like 8B, like this is just an 8B model. Like the results are like really interesting, just showing how better base model that is like really specifically designed on math with this RL, training it for longer stages, how much improvement we get. So this is quite crazy.
Is it AIME data set?
We are evaluating. This is still math data set.
Oh, it's just the math.
Just the math data. Yeah, okay. I have shown you this result. I want to break down these a little bit as well, just kind of how our results are compared. And again, as you see, we are evaluating on a really large collection of tasks on like reasoning, kind of knowledge recall, safety, and so on, and kind of keeping a good balance across all of them. Okay, so this is our model, the Tulu 3, all the kind of models, recipes, data, and so on are available. You can use it. And I also want to add this last slide, which is everything I've talked about here is about training and post-training, how to go from a base model to a good model that is able to do reasoning, okay? So here in our very recent paper, which is not integrated into Tulu recipe, we are actually working on that now. We started focusing on just math type tasks, math reasoning tasks. And then we started collecting a really, really high quality reasoning data and more complex math, okay? We started with initially collecting 60,000 examples and then did a lot of quality filtering. We ended up with 1,000 diverse samples and then generated kind of thinking, reasoning, a chain of thought, but with deep thinking kind of tokens by distilling from Gemini thinking model, and like basically yesterday we replaced it with DeepSeek R1 reasoning models, and then we did so up to here we just did SFT. We just trained a simple supervised fine-tuning model. We saw really good result. Okay,
this
and
was based on the Gemini distilled data.
This is based on Gemini distilled, but I didn't have time to put results here. Distilled from DeepSeek V3, DeepSeek R1, numbers are much higher even.
Okay.
This is the S11 number, as you see here. Okay, and then we just did a very, very simple, surprising inference time scaling method, which showed a really interesting result, where we let the model have some token budget to generate outcomes. Okay, and then we varied this token budget from 512 to 2048, or like for GPQA to 4096 and so on, okay? If the model hadn't met its token budget, we just added a kind of continuation token, in our case, weight, and then let the model think a little bit more. And with that, we saw that the model now is able to generate better and better reasoning trails. And it was very interesting. Again, a little bit more interesting fact, when we did not put any tokens, we just let the model generate more. We did not see this gain. When we used other tokens besides weight, again, the weights were not as good. So we are still investigating. Is it because of the alignment better with the fine-tuning data that we used and so on? So a lot of interesting questions here that we are exploring. Okay, so thanks a lot for inviting me. I just want to show you again this list of very interesting, important research problems that we still have in this domain. And this has not been possible without many people in my team who kind of led a lot of these efforts. Thank you.
Thanks, Hannah, for the excellent talk. And we learned a lot from it. And I also appreciate the openness of the whole entire research, not only open up the parameter, but also open up the whole training process. That definitely is very good for the community.
Yeah, we are very excited. Thank you.
Yeah. Do we have any question from the audience?
Yeah, I have a question. Hello, thank you for the talk. This is cool. Yeah, I've been following Nathan for a while, so this is really nice. So I just want to ask a question. So, I mean, there are many components in your pipeline, right? Like that led to the success. If you would pick one and isolate it and say that's the most important component that we should focus on, because I mean, there are many tricks and I think they're all kind of important, but which one you really think is what led us, to most improvement?
Yeah, that's a very good question. So I would say two things. I cannot pick one. So I would say data. Data is very important, and good data would help with, like, if you have really good data, you've already gone a long way in your SFT pipeline. Okay. So this is important. Again, we showed that same thing in our S1 paper. The second thing, the reinforcement learning, I would argue that especially for this type of reasoning test, when curating data is very hard, I would argue RL is this algorithmic advances in RL is very important, because in S1, I would say one big limitation of us is we distill data from either DeepSeek or from Gemini, right? If that data wasn't there, I don't think we could actually do the kind of this thinking behavior, right? But if distillation doesn't happen and we just have regular type of data, then RL is basically the solution, I would argue. And DeepSeek paper also has shown it to kind of add this thinking. And we saw actually some of that in our RLVR setting.
Okay, thank you.
Sure, good question.
Yes. Do we have anyone? Or maybe allow one more?
Can I have a question?
Sure.
Thank you for excellent presentation. And in your talk, data actually is one of the important techniques, right?
Yeah.
And I'm curious, what's your opinion or definition of high quality reasoning data? So is that about long thoughts or difficult questions with solutions?
Yeah. Very good question. I think this is a very interesting open research question. Okay, so I wanna say both. But if you asked me a few months ago, I would have said absolutely both. We really need high quality data. Otherwise we are we really need good high quality chain of thought data. Otherwise we are confusing our model. But now I have a little bit of second thought, because even though we saw that our chain of thought data was synthetically generated and probably noisy, okay? When it went through the RLVR stage, it has started kind of shaping up a little bit on kind of correcting itself on like not getting very much kind of like noisy because of the probably some noisy data that it had in its SFT data. Okay, so I think, or this is my intuition right now, that RL would fix even some of the noisiness that exists in the original SFT data. Okay, it shouldn't be bad, but okay, so this is one. The second observation we had was making higher quality data would make the data would lead to more data efficiency. Okay, like for example, we showed that with training on like 60K data and training on 1K data, almost similar results. So we probably didn't need those many data points that they were a little bit lower quality. Okay, so this is one question. The second one, I would say diversity is really important. Like we've shown it in multiple settings, like especially in all these kind of RL stages, when we bring in better, higher complexity prompts for the RL stage, this would let the model to kind of improve and kind of and make better kind of models over time. However, there is a balance. If you bring in super complex problems at the RL stage to an 8B model, it cannot learn anything from it. You probably confuse the model, right? So like depending on the model size, introducing new data that is suitable at that stage is really important. So there is a very interesting complex interplay between what type of data should be introduced at what stage. And I think somewhat like we are doing some of it, and I think people in the community should also look into that. It's very interesting.
Got it. Thank you so much.
Sure.
Yeah, great. Thanks, Hannah, again
Thank you.
for the talk.
Thank you
I
very
think
much.
people interesting, and then certainly can send an email and then take this continue have the conversation about this training.
Absolutely.
recipes.
Thank you.
Thanks.
Thanks a lot.